Hello, everyone. My name is Joanne, and I'm one of the community admins in the maintenance community by Upkeep. Thank you all for joining us today. If you're not already a member of our Slack group, we would love to have you join us. I'll go ahead and add the link on the right side here. Today we have Evan Zaboski joining us for a presentation on his part 2 of oil cleanliness, understanding filter ratings, and choosing the right one. I'll go ahead and let Evan introduce himself in a moment. So I just want to go over some quick housekeeping. The recording of today's session will be available in our Slack group tomorrow, along with a copy of the slides you see here today. Evan is also in the Slack group to answer any of your questions if we run out of time today. And if there's anyone else you know that would benefit from hearing from this webinar, please feel free to share this. And then you'll notice that your cameras and microphones are off as usual. What you'll do if you want to ask or answer any questions for Evan, you'll use the chat feature on the right side here. So feel free to chat your questions as they come up. We'll leave some time at the end to go over them. And any questions we don't get to, we'll go ahead and answer offline in the community as well. Well, that's all from me. Thank you again to Evan for being here and to everyone else for joining us. I'll go ahead and hand it over to you, Evan, to get us started.
All right, thank you. So yes, today's presentation entitled Oil Cleanliness Part 2. Part 1, essentially I introduced a 5-step plan for oil cleanliness, and I'd like to continue from there. So a little bit about me is that I am the Senior Technical Advisor at Test Oil, and as such I do a lot of training in this sort of field of reliability, lubrication, oil analysis in particular. And this 5-step plan is essentially the almost cradle-to-grave handling of lubricants. Really just doesn't cover quite the grave part, the disposal, but essentially it begins with delivery. You take delivery of new oil, and one of the first things you should always consider is that new oil is not clean oil, and therefore you should set a target cleanliness. And that is what we covered in Part 1, was establishing just how clean or not clean new oil is from new, and then how to establish a target cleanliness. So we'll talk about that target cleanliness in this section. Step 2 is, of course, once you take delivery, you're going to store it. Once you store it, you look for opportunities to clean it and possibly prevent it from getting any further contamination. Step 3, once you have it in storage, you need to take it out of storage to get to the machines. So you're going to, again, consider the same things. How can you prevent it from getting any dirtier? Is there any way you can possibly filter it while you're dispensing it? Step 4 is exclusion. That is dealing with keeping contaminants out of the machine. And basically in this step, you would look for ways to improve over the OEM breathers and possibly look for opportunities to add offline filtration. Where we're going to spend the time today is in the 5th and final step. We're going to talk about conditioning, in particular particulate conditioning. So we're going to refer back to that original target cleanliness and look for steps to achieve this. So with that being said, that's where we're going to focus. Step 5, how do we achieve our target cleanliness if we have or have not taken any of the other steps to prevent the lubricant from getting any dirtier? We're at least going to work towards it now. This is our last chance to make that improvement, so we're going to do so. Basically, in this section, I will discuss how to select filtration that is appropriate to achieving that target cleanliness. I may use terms like inline or offline. Inline is referring to the full flow, usually the OEM filtration systems. When I say offline, I'm usually referring to the bypass, or what some people call kidney loop dialysis. It goes by a variety of names, but basically secondary filtration that one might add to a machine that already has an existing filtration system, or for adding it to machines that do not have a filtration system and cannot accept one. So that being said, one other little note about filtration is that we could talk about filtration in ways that affect things like soft particles, the insolubles, the ones that lead eventually to varnish. And we could talk about filtration as it might relate to removing moisture from the fluid. But like I said, today we're just going to focus on the particulate side of it. So this shouldn't be a too terribly long webinar, so there'll be plenty of time at the end for questions. But essentially, to get us started, we could have a quick discussion about filters. When you consider a filter and all of its parts, we're going to really just focus on the media side of it, right? This isn't a filter talk. It's not meant to describe the different ways of constructing or materials used during construction of a filter. Mostly, we're just going to talk about the media that goes into the filter. So when we talk about the media, essentially the media falls into two very distinct categories that most of the filters are manufactured with. It's either being made from what's called a cellulose, or what some people term paper media, or the other type of media is something that's often referred to as a glass. So usually fiberglass or microglass are terms you might hear, or what many of us just call synthetic. The key difference between the two media types is the fibers, and the fibers being relatively coarse in comparison when you talk about a cellulose filter, compared to being relatively fine when you talk about a glass or synthetic type filter. Now, the reason that you would care about how coarse or fine the fibers are is that when you start looking at the overall media's performance, a cellulose or a paper filter being coarser fibers does not allow for as high of a density of pores per square inch, and those pores are harder to get small and consistently small. Generally yields a higher restriction of flow, and because this is a naturally occurring product, I mean, we're just taking wood pulp and squeezing it down into paper, you get a very random matrix of holes. It's much more difficult to control. By contrast, when we look at synthetic medias, we can get a much higher density of holes. We can usually get those holes consistently smaller, and what this yields is a very low restriction of flow in that same square inch of material. But the nice thing is, because this is an engineered product, we can actually taper the holes and have the holes on one side of the media larger than on the other side of the media. So the holes basically act like pinch points and can be a bit more efficient at their filtration. So by comparison, if you're to look at these two different types of media, both rated at exactly the same micron size, what the fibers being thicker or thinner do is essentially give you a greater density of holes. So if you consider that we're trying to filter out big red particles like you see in the graphic here, both filters would filter out the same size of big red particles, but as you can see, a paper element will have a much lower capacity and a higher restriction of flow. The synthetic media would have a much higher capacity, be able to take up more media, last longer, however you want to think of that, and do it while maintaining a higher flow rate until such time as it does become plugged. So with that thought in mind, there are two types of media, but there are also two types of filters. And when you describe filters, the terms we generally use are surface and depth, or what some people call pleated and stacked. With a surface or a pleated filter, what we do is we take one layer of media and we cram as much of it as we can inside of the cartridge or the filter housing. And to do that, we usually pleat the materials, hence why it's sometimes called a pleated filter. But with that, essentially, if you think about it, you have that one layer of media and the oil is going to flow through the surface of it, and that's why it's called a surface filter. When you consider a depth or stacked construction, what you're doing is you're taking one layer of media and you're putting another on top and on top and on top and on top. So you're stacking them. But then when you have the media, the oil now is flowing through the depth of the media rather than the surface of the media. So you get a much higher restriction of flow, but you get a much, much greater efficiency for that same media. So typically surface or pleated filters are used in inline flow, and depth or stack type filters are typically used in offline flow. Now that's not a hard and fast rule. It doesn't mean that it always applies, but just given some of the limitations of each technology, we tend to use the surface in inline flow because it does have a very high flow rate, and we tend to use the depth style in offline flow simply because it usually has a much lower flow rate. Now, the interesting thing before we move off of this is that either type of filter can be constructed from either type of media. So it's not to say that surface filters are always, paper and depth filters are always synthetic or vice versa. It can go either way. So with that thought in mind, when we choose a filter, we're not just choosing the media, we're also choosing the construction. And part of that comes down to what is the end application? What are we expecting it to do? Right? If we're expecting it to handle a high flow rate, well, we might favor synthetic over paper, or we might favor a surface over a depth filter. If we're looking for very high efficiency, on the other hand, we might be looking at a depth filter over a surface filter, but that doesn't necessarily mean we're going to pick one media over the other. Right? Just the basic filter type alone might give us what we're looking at, and we're indifferent about the media. However, in some cases, when we start dealing with different types of contaminants, water being a good example of one, we will favor synthetic media over paper media just because of the reactions that may take place that could compromise the filter. So with that, usually when we're talking about filtration, we're kind of assuming that we're talking about surface filters. That is the most common type that is out there. And so one of the things to note about a surface filter is to increase the capacity of a surface filter. We typically do things with the pleats to get a higher yield of surface area within that filter. So we can change the density of pleats, we can change the depth of pleats, and if we get really creative, we'll do a little bit of both and do what we call staggered pleats, as you can see in the bottom left picture, to fully maximize how much media is present inside of a surface cartridge or canister. Now, that being said, when you go to buy your filters, one of the key things we're looking at is the ratings. How are filters rated? And so let me show you an example of 3 different ratings. So all of these are rated at 5 microns. That's the same. So we've got a micron rating that's the same, but you're hearing terms like nominal, absolute, and a beta ratio of 100. And the question is, which one of those filters is the best? And depending on what you've been exposed to for information, some people believe that the term absolute means that it filters all the particles, as in absolutely no particle greater than 5 micron escapes that filter. And some people have therefore then heard that nominal traps some of them. Those definitions are not correct. That is not what absolute nor what nominal means. It's not like one means some and the other means all. They're very loose terms, as I will come to explain. As you will see, though, only the beta ratio is very clear as to exactly how good it is. So to answer this question of which of those 3 ratings is the best, let's look at what beta ratio is defined as. So beta ratio is a value that is obtained by an ISO standard called the multi-pass method. So remember that term, multi-pass method, because some people will find this a little bit confusing later, because what the multi-pass method reveals to us is something called the beta ratio. And the beta ratio is easily converted into something referred to as the single pass efficiency. And so when you hear the term multi-pass method and then you hear the term single pass efficiency, lots of people get confused or think they're 2 separate things, when in fact they're directly related to each other. The multi-pass method is a method whereby we run contaminated oil through a filter for multiple passes, hence why it gets called multi-pass method. But then what's determined from this is something called the beta ratio, which is a summary of how clean the oil becomes going through the filter in one single pass. So essentially we're running it multiple times and we're taking an average reading and reporting it back to you. Now it is called the beta ratio, but it is reported as a single number, which also sounds a bit confusing because most people would assume a ratio is one number to another. With beta ratio, the second number is always 1. So therefore we don't have to state what it is, which is why we can call a single number a ratio, because the ratio is assumed to be to 1. So what is this ratio then? What is this multi-pass method determining? Well, what it's determining is the number of particles that may enter a filter when only one of them will escape in a single pass. So when we talk about these particles, it's always particles larger than whatever the micron rating might be. So with the example on screen, it is a beta 5 equals 20. So that means 20 particles go in, 1 particle escapes, or the other way of looking at it is 19 out of 20 particles are trapped per pass. And the micron range is 5 microns or larger particles. So with the beta ratio, we can often easily see as the higher the number, the more efficient the filter is per single pass. The micron rating is what we're going to see will become the greater focus though, but I'll explain that as we go along. To get from beta ratio to efficiency, it's a fairly simple math calculation, but think of it before I show it to you. If I told you the beta ratio of a filter was 1, how good is that filter? Right? That means for every one particle that enters the filter, one particle escapes the filter. So as you can see, that's no filtration whatsoever. But if I told you the beta ratio was 2, that means for every 2 that go in, 1 escapes. Right? So that's 50% efficiency. Beta ratio of 3, on the other hand, this is where the math gets confusing, and people often think that means it's 33% efficient. The correct answer is it would be 66% efficient. If the beta ratio is 3 and 1 escapes, that means 2 out of 3 will be trapped per pass. So to see the math on this, I can show you the calculation. It's really just beta ratio subtract 1, because 1 will escape, divide by the beta ratio, and then multiply by 100 to get it into percentage. So with a beta ratio of 3, right, 2 out of 3 are trapped. So 3 minus 1 is 2. 2 divided by 3 is 0.66. Multiplied by 100, you get 66% efficiency. Hopefully that math is making sense. You can see by the table some other examples. But here's the key thing, something to note. When you're looking at beta ratio, like I said, a lot of people like to convert this to a single pass efficiency. So some people prefer the percentages off to the side. Other folks, and I'll just pick on marketing, not any one company directly, but marketing likes to avoid the use of hard and fast numbers because sometimes it makes the answer all too clear. So when you read down this list and you see, beta ratio of 1 is 0%, but beta ratio of 2 is 50%, essentially that's what the term nominal means. A nominal filter is a filter rated 50% or better. Now the better ends at 98.7%, which, as you can read down the list here, that's equivalent to a beta ratio of 75. Anything that is beta ratio 75 or higher is simply called an absolute filter. So the terms nominal and absolute are actually both, in fact, ranges that are not very well defined. So if we go back to this original question and say, which is the best filter? Well, now that you've seen the explanation for how you get from a beta ratio to an efficiency and how efficiencies are generally called by different names from marketing, we can appreciate that nominal just means anything from 50 up to 98.7% efficiency. Absolute is 98.7% or better, but the beta 100 is actually clearly defined. So you'll see that as 99% efficiency. So you know for a fact exactly how good the beta 100 filter is. You're simply told what range it is if you're given terms like nominal or absolute. So it's possible an absolute filter could be better than a beta 100, but there's just as good a chance that it's slightly worse. So think about that the next time you're looking at filters. Make sure that the beta ratio is clearly defined if you're looking at the efficiency of the filter. Now, when I say clearly defined, there are examples out there where it may or may not be as clear. If you look at the picture on the left, you can see that just by the magic marking of a Sharpie, we can change what this filter is rated at for micron rating, but it does clearly state the beta ratio is 200. So this one's been marked at 6 microns, so it's a beta 6 equals 200 filter. The example on the right is in some ways a little bit clearer and a little bit worse because it presents you the data in graphical form rather than just hard and fast written out as a numerical answer. But you can see that the micron scale at the bottom is 11.5 microns and 15 microns, and the beta ratios on the side are 200 and 1000. So if you just see where the data points land, you can read that as the beta 15 is 1000 beta ratio. The beta for 11.5 micron is 200 ratio. So there are ways that some filters are marked, and this is where it gets interesting, is that cartridge filters, spin-on style filters, both of those typically are marked in industrial applications. So a spin-on filter would be marked like you see in these images here. A cartridge style would be typically marked either on the seal on the end cap or sometimes printed directly on the media. And if not, sometimes it's printed right on the bag that they come in or even the box that they're shipped in. But for many of us, when we go to buy filters for our own personal vehicles and we go to whatever auto parts store that we like, we'll often find that is severely lacking. It'd be rare for you to come across a box, a filter whether on the packaging itself or on the filter itself, shows you any kind of micron rating. So I'll give you a little bit of an example of that in a bit. But right now, I just want to point out that typically you should, for an industrial filter, be able to find this information directly on the filter or its packaging. And of course, if you go to websites to order your filters, then you will definitely see the ratings there. It'll be partly part of the part number, will give you an idea what micron rating or beta ratio you're purchasing. But just to show that micron rating is far more important than the beta ratio, I'll show you a very old study that was performed. This study showed you that starting with a 25 micron filter, the blue line, the particle count, was quite high. Switching to a 5 micron filter, the particle count dropped. Now, if you look at the percentages along this line, that is the percent of the particle count that was metallic content. So you will see that not only did the particle count drop, but the metallic content dropped with it. And after some prolonged use of the 5 micron filter, the particle count reached very low values, relatively speaking, but the metallic content, the wear, disappeared. And just to prove it wasn't a fluke, they swapped out the 5 micron filter, put the original 25 micron filter back in, and the particle count jumped back up, and the metallic content also jumped back up. So it's one thing to focus on, beta ratios and get, the most efficient filter you can at any micron size, but the greater importance, of course, is always at what micron size are we filtering. And if you haven't did not participate in part 1, I encourage you to review or, rewatch the video for part 1, because it discusses how the micron rating that you're most interested in is clearance sized. And I gave a couple examples of what typical clearances look like, but essentially, with a lot of generalization here, you're probably looking at clearances that are 5 microns or less. So with that thought in mind, let's take a look at 5 micron filters. If I was to present to you some data and said to you that, hey, you can have a 5 micron filter, but you have 4 choices for beta ratio. You can choose a beta 1000, a beta 200, a beta 100, or just simply a beta 75. So from a marketing perspective, all 4 of these would be rated as absolute. But you are in fact aware of the beta ratio differences, and you're being told that the higher the beta ratio, the more expensive the filter is. You have to decide which filter do you really want to spend the money on. At what point is it economically feasible to buy the more expensive filter? So one approach would be to look at the efficiencies. Now, beta 1000 filter, if you do the math on that, is 99.9% efficient. If you're willing to go to a beta 200, you're dropping that down to 99.5% efficiency. So you're giving up 0.4% efficiency. Now, if you're saving half the money, that might sound like a pretty promising idea. What if you could get it cheaper yet by going to a beta 100? Well, now you're giving up about 0.9% efficiency. And as you can read, if you were to go all the way down to a beta 75, giving up only 1.2% efficiency, it doesn't seem like that much, given that you already have, or still continue to have, 98.7% efficiency. However, I'd like to present you with a slightly different take on this. Again, I'm not faking any of this data. This is all real. None of the math is being manipulated. But what if I was to show you how many particles would pass through that filter in just 4 passes? If you did the math on this, what you would discover is, compared to a beta 1000 filter, a beta 200 filter would allow 600 times more particulate to escape the filter in just 4 single passes. A beta 100 filter jumps up to 10,000 times as many particles will escape that filter in just 4 passes. And if you drop all the way to a beta 75 filter, the math will tell you that that's over 30,000 times as many particles will pass through the filter, not be trapped by the filter, in just 4 single passes. Now, like I said, in both cases, the math is absolutely correct on these. So where do you decide? Well, let me show you how you should approach this problem. Basically, if one takes the particle count and divide by the beta ratio for the filter at that same micron rating, so the particle count matches the micron rating of the filter. So we're comparing 5 micron and larger particles, considering that we're using 5 micron filtration. The particle count divided by the beta ratio will be the number of particles that you would expect downstream of that filter after 1 single pass. Because remember, the beta ratio is about single pass efficiency. So as an example, if I had a particle count of 10,000 particles and I was to filter it using a beta 100 filter at that same micron rating, 10,000 divided by 100, I would expect 100 particles to be downstream after one single pass. Now, if I was curious how many it was after 2 passes, I'd take my new particle count, so 100, divide by the beta ratio, also 100, and I would find that in 2 passes, that would get me down to 1 particle. So essentially, a beta 100 filter at the micron rating of my particle count in 2 passes could take me from 10,000 to 1, which is almost every single particle, right? That's got us down to practically nothing. So going back to the original question of the 5 micron filters and asking you whether or not you'd be willing to spend the more money to get the higher beta ratio and how important that may or may not be, let's do the math on this. Assuming that we have 1 million particles upstream that are 5 microns or larger, running them through a 5 micron filter of 4 different beta ratios, here's what we would get as a particle count after one single pass through the filter. So again, all I'm doing is taking 1 million and dividing by the beta ratio. These are the particle counts for each of the beta ratio filters. Now, if I take that number that's by the red bars and divide by the beta ratio again, I will be able to tell you how many particles should be there after 2 passes through the filter. And if I take those numbers and divide by the beta ratio again, I'll be able to show you how many particles should be there after 3 passes. And do it one more time with feeling, you'll get how many particles will be there after 4 passes. Now, if we look at the data, what does it tell us? Well, if we're being honest with ourselves, is the number that is represented by how many particles that will be there after 4 passes through the beta 75 filter, is that number 30,000 times higher than the number of particles that will be there after 4 passes through a beta 1000 filter? Well, yes, that number is actually 30,000 times higher. But what do we notice about both those numbers? They're decimals. Now, I don't know about you, but I don't think I can have a decimal of a particle. I either have a particle or I don't have a particle. So to me, any amount of particles that is less than 1 is essentially 0 to me at that micron size. So what I'm showing you is, in effect, all 4 of these filters were able to take a million count particle count and reduce it to less than 1. And like I said, I think less than 1 basically equates to 0. And therefore, what I realize is all 4 of these filters achieved the same end result after 4 passes. Now, if we just flip back through those for a second, you'll realize that actually a couple of these were able to do it in 3 passes. One of them was able to do it definitively in 2 passes, right? Get it down to 1 particle. So my point is, if you think about the micron rating being, the most important thing, and you choose that correctly, as you look at your filtration, it may take more passes to go with a lower beta ratio, as we can see by this data, but essentially we will still get there. So I think the best way to answer that original question of, is it worth more money to spend it on the higher beta ratio? If you are transferring your lubricants from point A to point B, right, you're taking them out of the drum and placing them into the machine, it may be worth more money to buy the higher beta ratio because you only get 1 pass and that's it. But if you're constantly recirculating the fluid because you've added in filtration, whether that is inline or offline, my point is, what you lack in efficiency, you will make up in passes. So ultimately, at the end of the day, as long as we get the micron rating for our filtration set correctly, and we have the time, the option to go more passes through the filters, you will still get the cleanliness that you desire. You will still remove the quantity of particles necessary to achieve your target cleanliness. You just need to make sure the micron rating will match your target cleanliness. Right? If you set a target cleanliness, as we discussed in part 1, of something like a 15, 13, 10 for an ISO code, well, the suggestion is you're going to need a 3 or a 5 micron filter to be able to achieve that. So what I'm saying is, if we used a 20 micron filter, picking a higher number, it wouldn't matter what the beta ratio was. We would never achieve it, no matter how many passes we gave ourselves, simply because we're not filtering down to a small enough micron size. I keep emphasizing that micron size is the most important part of selecting the filter. It's the one that will be aimed at achieving the desired cleanliness, but the desired cleanliness is driven by what are the clearances. So in that part one, I did refer to a statement from an SAE technical paper that said for engine lube oil systems, the critical particle size to control was between 2 and 22 microns, because those were the clearances in an engine. That same technical paper had two other conclusions to it. The first one here showed that compared to a 40 micron filter, the life or the wear, more directly, was reduced by 50% simply by upgrading to a 30 micron filter. And the wear was further reduced 70% by converting to a 15 micron filter. So it just is showing you how much better the cleaner fluid is at preventing wear when that micron rating is closer to the clearance sizes. So the third statement is just a summary of all that and basically says that the filter, its micron rating, as established by the single pass efficiency type test, is the most important factor when choosing a filter, right? And in this case, just being upfront and honest, an engine lube oil system will get multiple passes because it is constantly recirculating the fluid. So the emphasis becomes pick the micron rating that works best. Now, if you look at this graphic here and see how the data shook out, you can see that basically around a 10 micron filtration, as compared to a 40 micron filtration, you're getting about a 4 times life extension. That's pretty significant. And what was interesting is that that 10 micron value was one that was looked at and investigated by one of the major aftermarket automotive filter manufacturers. It was by Purelator. So I'd like to show you some data that Purelator once published. This is no longer on their website, but of course, when you see something good on the internet, you grab it while you can. But this is data I've had for a number of years that Purelator published, basically reviewing the single pass efficiency type test. Now, back when this data was produced, it was a slightly different version of the standard. It's since been replaced, but they evaluated filters at 10 microns. Now, stating this up front, this is a study sponsored, if you will, by Purelator. So it should be no shock to you when I show you the actual data, who Purelator thinks makes the best filter out there. But as you can see here, even though they rank themselves better than everybody else's filters, one of the things you gather from this is that ultimately, none of these filters are particularly efficient per single pass. But like I said, what they lack in efficiency, they make up in passes. So you circulate a fluid enough times through that filter, and of course in an engine lube oil system, you get hundreds of passes every time you operate the machine, you will eventually achieve the desired cleanliness and keep the fluid as clean as you'd like. So this just gives you some food for thought that, yes, you may think that there's a difference between filters in that, based on efficiency, you might think one of these brands is worse than another, but at the same micron rating, if they're able to remove particles down to that size, like I said, a lower beta ratio just means that they take more passes to get there. And in an engine lube oil system, like I said, you've got hundreds, if not thousands of passes to do this. You will keep your fluid as clean as you need to, which is why anyone who looks at this data and realizes that the brand they've always bought their whole lives are at the bottom of the list and go, but I've never had a problem. Well, this is why. It's not about the beta ratio. It's about the micron rating. And like I said, the disappointing aspect of it is we don't get to see the micron rating on aftermarket automotive filters. We only see the micron rating on industrial filters. So this being said, one of the most common questions I usually get about filtration, especially now that we've discussed that the micron rating is the most important part, is people ask, is there a micron rating that is too good, too fine? Where is the cutoff point? Obviously, you want a micron rating within your clearances, but is there such a thing as going too far? So little piece of background information about me is that for the last 12 years, it just ended a couple of months ago actually, but for the previous 12 years, I was editor of TLT magazine as a volunteer position. So something I got to do as a little extra kick, and that was be the editor for STLE's, the Society of Tribologists and Lubrication Engineers member magazine. And as editor, I got to write basically a column every month on whatever topic I liked. And that usually was about 700 words. And this topic of can filtration be too fine was a topic I did not think I could handle very well, not in 700 words. So one evening I was in Philadelphia and I met with one of my good friends and other writers, Neil Cantor, and I asked Neil if he would write the article. And the reason I asked Neil to do it is because we don't limit Neil's columns, so he gets like 3,000 to 5,000 words to do his. And Neil has all these great contacts within the lubricant industry and the additive companies. And in a previous life, I used to work at a filtration company, so I knew a fair number of good filtration contacts. And between these three sources, Neil put together a team of 16 people that he interviewed to write an article about this topic of, could filtration be too good? Could filtration remove additives? Was really where we were going with this, because that's the most common statement I hear when people ask about, is there such a thing as overfiltration? Basically, they're asking, can I remove the additives? Can I harm the lubricant? Now, from my chemical engineering background, I know that additives are typically on the nanoscale rather than the micron scale, meaning that they're 1,000 times smaller than a micron. So in my mind, I never saw how anyone could believe a even 1 micron filter would be capable of removing additives. But given our due diligence, Neil interviewed all these people at lubricant companies, additive companies, and filtration companies and asked them that question and got them to support their answers with some data. So long story short, out of the 16 people interviewed for the article, 6 of them were willing to answer that question. But they all answered it on condition of anonymity, so that means that there's no company names and no employee names. But anyways, they had to all agree as to what this answer was, because when we write articles for TLT, they get sent back to the interview sources for peer review. Basically, you get a chance to make sure you weren't misquoted, misrepresented, taken out of context, or anything like that. And what I'm about to show you are 2 quotes from that article to clearly address this question. And what I'm telling you is that this is as close to a peer-reviewed answer as you're going to get, because all the people involved in the article had to agree to the wording. So in the article, it states clearly that filtration studies on both new and used lubricants, done with hundreds of passes, there was no sign of additive removal. And just to save you reading all 6 pages of this article, down at the bottom, I put a note that they were using 1.2 and 3 micron filters during these studies. So there's simply no way a filter can be too good. There's no way a filter should harm the lubricant. And I know I've come across many people over the years after me stating that to them have said, oh, but I've heard, I've seen, or whatever it is. And they've almost always come up with some type of example. Most commonly, it usually is the anti-foam additive. For some people, it may be viscosity modifiers, but they can usually pinpoint a particular instance where the oil went through the filter and some of it was removed. And what I'll point out is the second statement that I'm showing you, quoted directly again from the same article. It says the ability of the filter to remove spent additives will, and the key word here is spent, will increase with contamination. So what we're getting at is, if your additives in any way have bonded or have an affinity for any of the contaminants in your oil, so usually particulate and water, if you filter out the particulate or if you absorb the water, well, in effect, you've also removed that additive. But understand that additive has already done its job by bonding with whatever the contaminant is, right? Like dispersants are specifically designed to bond with particulate in oil to prevent it from bonding with another piece of particulate, right? We don't want the particles getting larger. We don't want them agglomerating. So if your dispersants are bonded to particles, in effect, they're no longer effective. They've done their job. They did what they came to do. So if they're removed by your filter, well, that's neither here nor there. That will not affect the future performance of your lubricant. So typically when people have these stories, these examples of filters removing additives, it's because the additive has been absorbed through some other mechanism and therefore would not be worthy of any future consideration for the performance of the lubricant either way. So as much as I can state it over and over again, no, there's no such thing as a filter being too good. You cannot harm the lubricant through standard mechanical particulate filtration. Right? If you want to take the discussion into polymeric or ionic type filters, that's a completely different story, and there may be some effects there. But through the standard filters that we all typically think of, like I said, most commonly surface filters, the answer is no. But saying all that, there is one distinct possibility of harm that does come from filtration, And if you have not seen this before, this is called electrostatic spark discharge. And essentially what this is the phenomenon is if you take any liquid, it doesn't have to be oil, any liquid, water is a good example, and you flow it through an orifice. So your tap, your kitchen tap is a good example. You will generate static electricity. And so the thing about this is if you take a liquid and push it through an orifice at a higher velocity, you will generate more static. If you take the liquid and push it through a smaller orifice, you will generate more static electricity. So if you think about a filter, well, a filter is basically millions of tiny orifices. You can generate static electricity. And the point is, and the problem is that sometimes you will generate enough static that it will self-discharge. So basically, if you recall, when you were younger, most of us did this when we were younger, you would shuffle your feet on the carpet and you'd sneak up behind somebody, usually a sibling or a cousin or somebody like that, and you'd get your finger right behind their ear and you'd touch them right there, and they get zapped. And of course, you wouldn't feel anything, you just, slight tickle, but it would hurt them. It's because that little static discharge was actually a high temperature miniature lightning bolt. And in the world of lubricants, that static discharge has been tested to be over 10,000 degrees Kelvin, which is hotter than the surface of the sun. It's just really, really, really small. It's microscopic. But in that very short path of that electricity, that static discharges arcs, it will burn whatever's in its path. So in this case, hydrocarbon molecules from the oil. And so what you get is with repeated static discharges, you get repeated burnings, which are fairly incomplete combustion of your oil. And this will produce carbon particles. So if you've ever seen a fluid have rapid darkening and you thought you couldn't explain it, generally the phenomenon is either microdieseling or electrostatic spark discharge. And if you know you've got the lubricant flowing through orifices, and like I said, in particular, a filter is a good source of a bunch of orifices, then the possibility that it's electrostatic spark discharge starts to rank probably higher than it is for microdieseling. So if you look at this picture in the bottom right, you will notice it's of a filter. And if you know things about filters, you probably know that the end caps are made out of typically some sort of stamped metal, some tin or aluminum type looking metal. Well, the center tube down through the middle of that filter is of the same material. So what I'm saying is the picture should look silver down through the center, and you're noticing it doesn't. And if you know about the direction of oil flow through a standard filter, it is from the outside in. So the fluid that's down the center of that filter should be the cleanest fluid because it's passed through the media. But in this filter, you can tell that as the oil passed through the media, it generated static. That static discharged probably on the center tube. That's probably where it got grounded, and it burnt the oil, creating carbon particles that were, polar. So they were agglomerating on the clean side of that center tube. So that's why the center tube has become black. It's coated with all these burnt oil particles. So that is one possibility of overfiltration, of filtration being quote unquote too good, right? Is if you suddenly take a filter and change it to a much lower micron rating, thereby restricting it, giving it more orifices, you may have given yourself the circumstances that could create the static. So electrostatic spark discharge is a possibility. I'm not saying it's a guarantee, but it is something that people have encountered when they've just arbitrarily changed a micron rating of their filters to something significantly lower and not taken in these considerations of what does it do to the back pressure, what does it do to the flow rates, and will it actually generate the static? So there are a couple of solutions around this. One, of course, is just not do that, right? Don't pick finer micron ratings without consulting anyone. But another possibility is if you want to support going to a finer micron rating, you can purchase filters specifically created to help discharge the static before it builds to these damaging levels. So sometimes they're interwoven with conductive materials, thereby it reduces how much static can be built up in any one moment in time. So that being said, essentially I'm at the end here. Really what I'd like to say is that understandably, looking at filtration or just lubricant cleanliness in general is what we call the low-hanging fruit, right? To use an overused term, but it's basically comes back to the Pareto principle that probably 80% of your lubricant concerns can be handled by 20% of the effort, and that effort's going to center around the cleanliness. So considering instituting or improving existing filtration practices is generally one of the most easily and implemented and most easily assessed ways of improving a lubrication system. You can generally show a close tie between improved cleanliness and less wear, greater uptime, longer performance, longer lubricant life, drain intervals, all the different metrics that people have for measuring their lubrication program. But my caution is always, always, always consult your filtration experts. Right? Talk to the people at your filter companies before suddenly switching out your filters for something different. Right? Make sure that what you're buying is compatible with the oil, gets the desirable flow rates, doesn't have too high of a back pressure. If you've got concerns about electrostatic spark discharge or some sort of conductance issues, again, all these questions can be addressed by talking to your filtration experts. What I'm really saying is don't just go on Amazon or whatever other, web-based retailer that you can find that simply sells filters of the correct dimensions and just buy whatever you think is the smallest micron rating with the highest beta ratio because it sounds good. Right? Make sure you have all the other considerations in place before you make these changes. So with that, I'll end here, and I've got my email address up if you are looking for a way to contact me, but I'll take a look now, see if there's any questions that have been asked, and turn it back over to Joanne.
Thanks, Evan. Yeah, we do have a few questions here, all from the Reddit. I'm not sure if you see it, but I can go ahead and read it out to you. First question is, at what micron and beta ratio would additive be at risk to be filtered out in engine and gear oils?
Well, as I said, additives are on the nanoscale. So they're 1,000 times smaller than 1 micron. And as I showed, the direct quotes showed 1.2 micron filters did not remove additives from neither new nor used fluids of different base stocks. So what I'm saying is, without giving you a direct answer, because I don't want to be held to it, there's no filter on the planet you could buy that fits an automotive application that would strip out additives, simply put. Now, if you were to go and try and build your own, you could go to submicron filter paper, right? 0.1 micron filter paper is readily available. You could build a filter out of 0.1 micron filter paper. I'm still fairly confident you would not strip out your additives. I just can't see how it's possible. You're still an order of 100 times larger than is typical of additive sizes. Just to give an example, ZDDP, right? The zinc dialkyl dithiiophosphate, that's one of the more common additives in engine oils. That is on the order of 0.0005 to 0.0007 microns across. So 5 to 7 thou of a micron in dimensions. So you're not going to strip that with a 1 micron filter, even if you could find a 1 micron filter, engine oil filter, which I have my doubts. So there you go.
Awesome. I'm not sure if this answered this question as well, but another question was, why do water separator filters not use the beta ratio?
Well, the simple answer is because the beta ratio is designed for evaluating how much particulate is removed from oil, not water. So water separator filters typically use what we call an oleophobic hydrophilic media, meaning they hate oil, they love water. The media is meant to absorb the water onto the media itself. It's not rated for its pore sizes. So beta ratio simply just does not apply to a coalescing or desiccant type filter media. And typically they're actually harmed by particulate getting into them. So usually you put a particulate filter upstream of water separation media to prolong the life of the water separation media. But the short answer is there's no rating because it wouldn't apply.
Cool. And how does oil flow pulse affect the filtration ratio?
Well, understandably, if there's any pulsing of the oil pressure, that is different because the multipass method is a controlled flow rate at all times during the testing. By pulsing, obviously, you're going to wander into the territory of potentially lower rates, but the beta ratio is reported under standardized conditions. I guess the easiest way I'd have of saying this is, if you think about something very simple about oil, like viscosity, right? It's a very commonly reported physical property of the lubricant. Well, viscosity is tested at a standardized temperature of 40 or 100 degrees Celsius. So when you look up the viscosity of any oil, any product data sheet, you're going to find the viscosity rated at either or both of those two temperatures. Well, that never tells you what the viscosity is at another temperature. It never tells you what the viscosity is under different pressure, because it's always tested at atmospheric pressure, right? It's just a standardized way of giving you comparison data of this is this oil's property under these conditions. You may compare it to other oils and know that the conditions remain the same. So beta ratio is a standardized measurement the same way, saying, look, under the same circumstances, this is how it rates. So if you're trying to compare it to a different filter, you can make those comparisons. When you start wondering about how does it behave once it's in service, well, your service will be a different viscosity fluid at a different flow rate, at a different pressure. So all these things start to affect what the actual number would be. I think if I'm understanding the question correctly, if you had pulsation of the pressure during operation, that adds yet one more variable. So yes, it would change, it would get worse. But again, the beta ratio is to report it at a under standardized conditions.
Got it. Thank you for explaining that. And then we just have one last question here from Karen Deep. Is there a rule of thumb for return line filter in industrial hydraulic units?
Kind of wondering what type of rule of thumb they mean. If I was to offer a rule of thumb that I know exists when people are trying to do things with filters, and this is a very rough rule of thumb, hence the name rule of thumb, is that one of the rules of thumb we have for determining how many passes is a real pass. The rule of thumb is 6, is basically the fudge factor. So what I'm getting at is this. If we were to talk about a drum of oil, right, 55 gallons, and we're to use a 5 gallon per minute pump, the math on that tells me in 11 minutes, we will pump 55 gallons of oil through the pump. Now, if we put a filter downstream of the pump, then some people would argue that in 55 minutes, we would circulate all 55 gallons through the filter. And the rule of thumb is that it actually takes 6 times longer than you think. And it's because when you're recirculating oil, you're not doing an A to B transfer. You're not taking all the oil out of one drum, pumping it through one filter into another drum, and thereby you're guaranteeing all 55 gallons have gone through that filter. When you're recirculating, and this is, I hope I'm interpreting the question correctly here. When you're recirculating, we add a fudge factor of 6. So we say, look, if we think it's going to take 11 minutes because 55 gallons at 5 minutes, 5 gallons per minute is 11 minutes, we'd multiply that 6 and say 66 minutes, that it would take just over an hour of constant recirculation of taking oil out of drum A and returning it into drum A before we actually achieved the theoretical equivalent of one true single pass. So if we're doing that calculation like I showed, figuring out how clean will the fluid get in a single pass, there's a fudge factor of 6 multiplying that in a recirculating system, because you're not changing over the fluid as efficiently as if you're transferring it from A to B. So I hope that answers the question, or had the person rephrase it.
Yeah, just a response to your answer here. Clarified saying that this will be a return line on a hydraulic system, for example, a single pass. So would you recommend 5 micron, 10 micron, or 1 micron filter?
So the best answer I could possibly give that question is you should rewatch part 1 of this series, because what it determined was your clearances are what governs the micron rating. And I'm just going to say, as a rough rule of thumb for a hydraulic system, what you're probably going to find is, yes, 5 microns or better. 3 is probably quite good as well. Wouldn't necessarily think 1 is required, but if you're talking about full flow on a return system, so your oil's returning to the tank, then like I said, you will need to talk to a filtration expert, because it's possible that even a 5 micron filter may produce too much back pressure going into the tank, that you're not going to get the oil flow into the tank, and you could cause a low fluid level just because of that. But based on clearances for a typical hydraulic system, you're usually looking at 5 microns or better as your filtration. Now, that is probably more pointed towards your supply filters if you do have separate filtration for the oil leaving the tank before it goes to the hydraulics than you do on the return line side. So again, talk to your filtration experts. That'll give you the best possible answer. And I would encourage you, yes, to review part 1 because it goes through how to select the micron ratings for filtration.
Perfect. And then one more question here. How is dirt holding capacity determined in filters?
So the multi-pass method, which was the ISO 16689 test, is the same test that we use to determine dirt holding capacity. And that is basically figuring out how much dirt by mass the filter can hold before it reaches terminal differential pressure. So we do use the same test method. It is the same multi-pass method at arriving at the dirt holding capacity. So if you're curious, just look up that ISO standard and it could explain it in great detail how the testing is done if that's really what you're looking for. But ultimately, it's kind of a theoretical number for how much dirt it will hold by mass. And as I always point out, it's standardized dirt. It's if you buy a filter and one's rated at 400 grams and the other one's at 600 grams, my first question always is, what size dirt, right? Is this 10 micron and larger dirt? Is it 5 micron and larger dirt? But it's basically, manufactured dirt. We have to control the contamination when we do the multi-pass method. So we use standardized materials to do so. So does that technically relate to 400 grams of the airborne contaminant you have near your system? Maybe it does, maybe it doesn't, but it probably won't compare to somebody else's system who has different environmental particulate. But long story short, it is the same test that's used to determine dirt holding capacity.
Awesome. Questions keep coming in. We have one last one. I think this will be the last one before we wrap up. Ahmed asked, what is the main criteria are the best to select a filter for heavy duty diesel engine oil?
Wow. These questions are almost like they're set up, so I keep plugging the first one. But the part 1, in that I showed that for the study that was done at the time, that the critical particle size that was controlled for engine lube oil systems was slightly larger in the 2 to 22 micron range. So typically when you look at the automotive style, diesel engine style filters, they're rated around 10 or 12 microns, could be quite common. They don't have to be quite as fine as we would use, like the other question that was asked about the hydraulic system. But, when anyone asks me about, in particular, mobile equipment type applications, there's almost always an OEM recommendation. And that OEM recommendation is there for a reason, because it's not just, in cases like this, it's not just about a micron rating. It's also about the orifice sizes in the filter to achieve the desired flow, because you are counting on that filter delivering full flow oil flow. So therefore, you're curious about what's the bypass spring rated at, because if you don't get the flow, well, that filter will go into bypass, right? If there's too much restriction of flow, the filter will go into bypass, which means it's not filtering. And then the other consideration is in some of these applications, those filters have check valves in them. So if you start just, again, pick on Amazon, but pick on any web retailer, if you simply go online and look up filters that fit the application, that's all they're guaranteeing. They will fit. They have the right O-ring dimensions, they have the right thread size, and the overall, casing on the spin-on filter may fit that application. And it could be rated anything. I mean, you could buy good or bad filters that way. But my point is there's more considerations to that filter than just the micron rating. Right? You are looking at other aspects to it. So I would be hesitant to move away from any OEM recommendations just because, like I said, there's more to it than you think. So it's not just about what micron rating should I buy, right? If it's a big, diesel engine, it's probably a Caterpillar, a Cummins, a Detroit, or a Deutz, or whatever brand it happens to be. They'll have the recommendations for the filters, and there will be options, right? The Magnuson Warranty Act of 1975 says you're not beholden to buy the OEM branded parts at all times. They have to give you an equivalent. So that would be my cover your butt answer to that question, is look up the OEM specs first before delving too far down that path of what's the micron rating I want.
Awesome. Thank you, Evan. Well, that concludes our webinar. It's just about 12 p.m. over here. Thank you for spending your time hosting this webinar and answering all of our community's questions. It was a pleasure having you with us. And I thank everyone else here for attending. We hope you learned something new and enjoyed the webinar. And again, Evan and I are in the community Slack group. Please do not feel free, please don't hesitate to reach out if you have any further questions. The recording again will be provided tomorrow in our Slack group. Any last words, Evan?
No, just thank you for having me. And yes, if you do have any other questions, please just reach out.
Thank you so much, Evan. See you everyone in Slack. Have a great day.